Howdy. This video is on standard electropotentials. For electrochemical reactions, the electropotential can be used to determine if a reaction is spontaneous or non-spontaneous and is related to delta G naught K and delta S of the universe. For reactions with positive potentials, the potential is equal to the amount of volts that the reaction can produce if made into a battery. If the reaction has a negative potential, then the potential is equal to the voltage that has to be applied for the reaction to actually proceed. After watching this video, you should be able to determine the potential for a reaction from the corresponding half reactions. You should be able to determine the potential delta G naught K for a reaction when it is reversed or its coefficients are multiplied by a number. And given one of the following three parameters, E, delta G naught, and K for a reaction, you should be able to determine the other two. For electrochemical reactions, we can typically define a standard potential. Standard potentials are defined under standard conditions, which mean all soluble species are at 1 mole per liter. Slightly soluble species must be at saturation. Any gas is constantly introduced at 1 bar. Any metal, it must be in electrical contact. Other solids must also be present and in contact. These are the same standard conditions as defined when talking about thermodynamics, when we talked about delta G naught standard, delta H standard, except for the metal being in electrical contact. Standard potentials of half reactions cannot be measured independently. They have to be measured relative to another half reaction. And so we can't determine it in absolute terms, and so we define the standard half cell as having zero potential. And our standard half cell is hydrogen ions plus the electrons going to hydrogen gas at 1 atmosphere or 1 bar. And so the standard half cell looks something like this. The platinum is actually where the reaction occurs, but it's not involved in reactions, neither consumed or produced. It's just where the reaction occurs, and platinum is typically used because platinum is not very reactive. This is the standard half cell, and the potential is defined as being 0. Now for the non-standard potential, that actually does depend on concentration. And so we can actually determine the non-standard potential using a Nernst equation. The non-standard potential is equal to standard potential minus RT over NF natural log of Q. And so E is the measured potential, the non-standard potential. It depends on concentration. E naught is the standard potential. It's independent of the concentration. It's specific or specific reaction at a specific temperature. R is the gas constant, T is temperature in Kelvin, N is number of electrons being transferred, F is Faraday's constant, and Q is the reaction quotient. Remember, products over reactants, coefficients become exponents. Pure solids, pure liquids do not appear. And so we saw previously that delta G naught equals minus RT natural log Q, and we see here that delta G naught equals minus NFE. And so delta G naught, K, and E naught are all constants for a specific reaction at a specific temperature. We also saw previously that delta G equals delta G naught plus RT natural log Q, and delta G equals minus NFE. And so delta G non-standard, Q, and E do change as the reaction proceeds. So typically for electrochemical reactions, standard potential can be defined. If the potential is positive, that is the voltage that the reaction would produce if made into the battery. If the potential is negative, that is the voltage that would have to be applied to force the reaction to occur. And so here we have silver ions plus copper metal going to silver metal plus copper ions. Its potential is plus 0.46 volts. And so if we made this into a battery, that's the voltage we should measure. Now, if we flip it, so we swap products and reactants, that changes the sign of the potential. Now the potential is a negative 0.46. And so in this case, this reaction would not proceed spontaneously. We would have to force it to occur by applying a potential greater than 0.46 volts. And so delta G naught for electrochemical reaction can be determined from the standard potential. Delta G naught equals minus NFE. If we solve for E, we get E naught equals minus delta G naught divided by NF. And so to me, this equation is pretty helpful. So it tells you that E naught is actually per electron because you're dividing delta G naught by the number of electrons. And so you should be able to calculate E naught from delta G naught or delta G naught from E naught. And so for this one, we had a potential of 0.46. And so delta G naught equals minus NFE. Now our copper is going from 0 to plus 2, so there's 2 electrons in the oxidation half reaction. our silver is going from +1 to 0. And so each silver is gaining 1 electron. We got 2 silver, so that gives us 2. And so the number of electrons oxidation half reaction equals number of electrons reduction half reaction is equal to the number of electrons transferred. And so we have 2 electrons being transferred for the reaction as written, times Faraday's constant, 96,500 joules per volt mole, times our potential of 0.46, and we get a minus 89 kilojoules per mole. Now, please remember, negative delta G naught corresponds to spontaneous reactions. Positive E naught corresponds to a spontaneous reaction. The constant for electrochemical reactions can also be determined from the standard potential. And so we've seen that delta G naught equals minus RT natural log K. We've seen that delta G naught equals minus NFE. And so that tells us that RT natural log K should equal NFE. So we combine those two equations, get rid of the negative sign. Now we can divide by RT. Now if we take everything to the power of E, we get that the Eckman constant is equal to E to the power of NFE over RT. And so it's kind of cool. We can actually calculate the Eckman constant directly from the potential. And so again, if we look at the reaction we were talking about, we have a potential of 0.46. And so we saw that there was 2 electrons being transferred times Faraday's constant, 96,500 joules per volt mole, times the potential of 0.46, divided by the gas constant, 8.3145 joules per mole Kelvin. So the joules cancel. Times 298, so Kelvin cancels. And there should be a mole in the 2, so the moles would cancel. And remember, everything to the power of something else should be unitless. And so notice also the volts cancel. And if we plug that in, we get 3.6 times 10 to the 15th. And so we saw that we had a positive potential, we have a negative delta G naught, and a K greater than 1. Those all mean spontaneous reaction.
To demonstrate the copper-silver oxidation-reduction reaction, we're going to place a piece of copper wire in a petri dish and add silver nitrate solution to it. Here we can see the silver crystals beginning to grow, causing the copper wire to look gray and fuzzy. The copper wire you see under the microscope appears slightly out of focus, but as the silver crystals begin to grow and grow towards your eye, they will sharpen and become in focus. As the growth process continues, you begin to see the bright metallic crystals of silver metal. Here we see the contrast of the original copper wire to the wire after it has been in the silver nitrate solution. You'll also notice that the solution has turned from clear to pale blue. The copper metal has become the copper 2+ ion in solution, resulting in the blue color. The silver ion solution has become crystals of silver metal.
So again, potential for this reaction is positive, delta G naught is negative, and K is greater than 1, meaning this reaction is spontaneous. And so if you put a piece of copper in a solution of silver ions, you'll actually produce silver metal and copper ions. And so when the potential is positive, delta G naught is negative, K is greater than 1, we'd say that reaction was product favored. You could use it actually to convert chemical potential energy into electrical energy. If the potential is negative, then delta G naught would be positive, K would be less than 1. It would be a reactant favored reaction. We'd say it's non-spontaneous. Remember, in this context, spontaneous just means occurs without any outside intervention. Non-spontaneous means does not occur without any outside intervention. So we can go from E to delta G naught and delta G naught from E. We can also calculate the Eckman constant from delta G naught or from E. So we saw that E naught is equal to minus delta G naught over NF. And again, this means that E naught is per electron. And so if we multiply a reaction times the number, the E naught doesn't change, but our delta G naught does. So we multiply this reaction times 2. And so we have to multiply delta G naught by 2, but E naught does not change because, again, it is per electron. So for delta G naught, if you multiply reaction times a number, you have to multiply the delta G naught by the same number. Now for K, if multiply the reaction times a number, we have to take K to that power to get the new Eckert constant. But again, for E naught, because it's defined per electron, multiplying reaction times the number does not change E naught. Now if we swap products reactants, that changes the sign of both E naught and delta G naught. If we swap products reactants, remember you have to take the inverse of the Eckert constant to get the new Eckert constant. And it just changes the sign of your E naught. So standard potentials are for a reaction typically determined from the corresponding oxidation and reduction half reactions. And so this is our oxidation. Remember, Leo goes Ger, lose electrons oxidation, gain electrons reduction. And so electrons will always be in the product side of an oxidation half reaction. Electrons will always be on the reactant side for the reduction half reaction. Now, if we add these two reactions, we get this reaction that we're looking for. And if we add these two half reactions, we add the corresponding potentials. Now, you can only add potentials, or you can only add reactions when you have the same number of electrons. And so we have 2 electrons here and 2 electrons there. Remember, electrochemical reactions, you have a transfer of electrons, so you need to have the same number of electrons in your oxidation half reaction and your reduction half reaction. Now, typically, tables of half reactions will just be for the reduction half reaction. And so again, remember, Leo goes Ger, lose electrons as oxidation, gain electrons reduction. And so for reduction, electrons are always in the reactant side. Now, if we want to determine the oxidation from reduction half reaction, we just flip it. And so if we look at this half reaction down here, it's a reduction half reaction. We're going from magnesium plus 2 electrons going to magnesium metal. Now, if we want the oxidation half reaction, we can flip it. And so we have magnesium metal going to magnesium ion plus 2 electrons. If you flip the half reaction, you change the sign. And so reduction potential for magnesium ion is minus 2.36. The oxidation potential for magnesium metal is plus 2.36. And again, please remember, half reactions cannot be measured independently, and so they're always measured relative to the standard half cell, which is hydrogen ion going to hydrogen gas. The standard half cell potential is defined to be 0. Finding the standard half cell as having 0 potential is similar to how elements in their standard states are defined as having 0 enthalpy of formation and Gibbs free energy formation. Remember, we cannot determine enthalpy of formation or Gibbs free energy formation in absolute terms, and so that's why we define elements in their standard state as having 0 enthalpy of formation and Gibbs free energy of formation. And so the more positive the potential, the more likely the reaction will occur. And if we look at the table, of those on the table, F2 is the most readily reduced. It has the largest reduction potential, 2.87. And magnesium metal is more readily oxidized because it's going to have the largest oxidation potential. And so again, remember, to get the oxidation potentials, you have to flip the reactions, which would change the sign of the potential. And so the oxidation potential for magnesium metal is plus 2.36. And so looking at the table, we get that magnesium 2 plus going to magnesium metal, you have a reduction potential of 2.36. If we flip the reaction, putting the magnesium metal as a reactant, and so magnesium metal going to magnesium ions plus 2 electrons, that would be a plus 2.36. And so that would be the oxidation potential for magnesium metal. Now we could ask, okay, what's the oxidation potential for magnesium plus 2? Or what's the reduction potential for magnesium metal? Now, those values are not given in the table. And, the magnesium plus 2 is not really oxidized. It doesn't want to lose any more electrons. Magnesium metal is not typically reduced. It's not going to gain any electrons. So we do not know the oxidation potential for magnesium plus 2 ions or the reduction potential for magnesium metal. In general, nonmetals react by gaining electrons, hence they have positive reduction potentials. In general, metals react by losing electrons. And so if we flip these, we'll tend to get positive oxidation potentials. And again, remember, the more positive the oxidation potential, the more reactive the metal. Metals with negative oxidation potentials are less reactive. Gold is the least reactive metal in the table above. platinum, silver are members of groups referred to as noble metals because they are less reactive. Metal ions tend to get reduced because they tend to gain electrons. Removing more electrons from them is not energetically favorable. And so we could ask the simple question, which will more readily rust, iron or magnesium? And so here we got iron, here we have magnesium. Rust is just oxidation, and so we need to flip it. And so magnesium has a oxidation potential of plus 2.36. Iron is plus 0.44. And so actually magnesium is more readily oxidized. It will rust more readily. Because of that, magnesium will be used as a sacrificial anode. And so if we look at, if you have a steel pipe in the yard, often what they'll do is they'll solder a wire to a magnesium slug, and then the magnesium will preferentially oxidize instead of the steel pipe. In your hot water heater, you also probably have a sacrificial anode, and so it's going to be either aluminum or magnesium. And again, the idea is the anode will oxidize instead of your water heater oxidizing. So we can ask, is the reaction below spontaneous or non-spontaneous? And so when you ask this question, what you want to do is you want to come up with the oxidation half reaction, the reduction half reaction, add those two to see if the potential is positive or negative. And so we have chlorine gas, Cl2, and so we'll use this reduction potential. Zinc metal, and so we're going to have to flip this reaction. And so we flip the reaction, it changes the sign from minus 0.76 to plus 0.76. We add the half reactions. Remember, you have to have the same number of electrons. When you add the half reactions, you add the potentials, and so we get a potential of 2.12, which means that the reaction is spontaneous. A positive potential means you have a negative delta G naught, and you'll have an Eckham constant greater than 1. We can try another one. So for this reaction, we have iron plus zinc ions going to iron ions plus zinc metal. And so we have iron. And so here we need iron as a reactant. Here iron is a product, so we'll flip it. And so that will give us a plus 0.44. Here we have the zinc ions, and so that's a minus 0.76. And so plus 0.44 minus 0.76 gives us a potential of minus 0.32. And so our negative potential corresponds to a positive delta G naught, which means that this reaction is going to be non-spontaneous. Our Eckham constant would be less than 1. And so we can determine if a reaction is spontaneous or non-spontaneous by just calculating its potential. And so here we have a series of metals and ask which one of these metals will spontaneously react with hydrogen ions. And so hydrogen ion, this is our standard potential. And so you can imagine if we take this half reaction, flip the one right above it, that would give us a negative potential. And so we'd imagine that hydrogen ions should not react with silver metal. If we look at the iron, if we flip this one, that changes the sign, and we'll get a potential of plus 0.44.
Equal amounts of magnesium, aluminum, iron, and zinc are each covered with 100 milliliters of concentrated hydrochloric acid at room temperature. As the acid begins to react with the metals, hydrogen gas is liberated, and a solution of the chloride salt of the metal remains. Also, the temperature begins to rise. Because we have used the same amounts of metal for all the reactions, we can compare them. It is apparent that although the reactions are similar, they liberate different quantities of heat and proceed at different rates.
And so what we should expect is that all these metals except for silver will react with hydrogen ions. And again, if we look at the potentials for those reactions, we see that the potential for the one with silver is negative, so that's a non-spontaneous reaction. For hydrogen ion plus iron, plus zinc, and plus aluminum, these are all positive potentials, and so those reactions will be spontaneous. We can add another interesting question. Will a modern penny, which is copper-plated zinc, dissolve in concentrated HCl? Now, when you ask about questions about HCl, use this potential here, hydrogen ion plus two electrons going to hydrogen gas. The chlorine in HCl is going to be chloride ions. And so here it's written as a product. If we flip this reaction, we'll get negative 1.36. And so remember, the more positive potential, the more likely, more negative the potential, the less likely. And so we're not going to worry about the chloride ions because it has a negative potential, just about the hydrogen ions. And so hydrogen ions plus the copper metal, that should give us a negative potential, and so that would be a non-spontaneous reaction. Now it's kind of interesting, if we look at the zinc, if we flip the zinc one, we see that HCl should react with zinc metal. That would give us a positive potential. And so what you could do is, if you had a copper plated zinc penny, if you scratch away some of that copper on the edge and leave it in hydrochloric acid, what's going to happen is the zinc inside is going to be reacted with, and you'll be left with copper foil from the outside. And so HCl will react with zinc. It will not spontaneously react with copper. We could ask the same thing about nitric acid. And so nitric acid is HNO3, and so you have hydrogen ions and nitrate ions. Now if we take this half reaction and we add it to the copper reaction after we flip it, we get a positive potential. And so nitric acid will dissolve copper. And so electrochemically, not all strong acids behave alike, right? So HCl, we use this half reaction. For nitric acid, we'd use this half reaction. Nitric acid is able to react with copper. HCl is not able to spontaneously react with copper. And so not all strong acids are the same. Again, electrochemically, they could be different. And so if you're asked about nitric acid, you use this one. If you're asked about perchloric acid, you use the one in red. And so the perchloric acid actually can dissolve more things than nitric acid. And if you're asked about just any strong acid or HCl, you use the half reaction in blue. So we could ask ourselves, is there any way of dissolving gold? And so gold is up here. If we flip this reaction, that would give us a minus 1.52. And so the perchloric acid actually is not able to spontaneously react with gold. Nitric acid, not able. HCl, not able. All those will give us a negative potential, meaning it's a non-spontaneous reaction. Now what we could do is, if we react with gold, some nitric acid, and so we can get a little bit of the gold into solution, then we can actually add some chloride ions. And the chloride ions will form a complex. And so if we're able to consume some of these gold ions, then this reaction will keep on going to the right. This is just an example of the Chatelier's principle. And so you can dissolve gold using aqua regia, which is just a mixture of hydrochloric acid and nitric acid. And again, you can think about this in terms of Le Chatelier's principle. You're getting a little bit of the gold ions into solution, and then you're complexing them. And so you're moving some of the products, pushing this reaction farther to the right. So for electrochemical reactions, you can tell whether or not a reaction is spontaneous or non-spontaneous by the potential. If the potential is positive, then delta G naught is negative. K will be greater than 1. It will be a product favor reaction. You can use this reaction to convert chemical potential energy into electrical energy. If the potential is negative, then delta G naught is positive. It will be a non-spontaneous reaction. K will be less than 1. It will be reactant favored. And if you want, you can try to force this reaction to occur by adding electric potential and converting electrical energy into chemical potential energy. And so E naught, delta G naught, and K, they're all constants for a specific reaction at a specific temperature. And given one of them, you should be able to determine the other two. And remember, the potential is relative to our standard half cell, which is hydrogen ions going to hydrogen gas. I hope that was helpful.